Okay, so we went over looking at how to name some stuff. Now we're going to look at empirical formulas. This is just simply what would the formula look like? Say that you had, in this case, looking at this one, a +2 and a -2. Now we already know about the crossing it over, right? So O2 or O is -2, magnesium's +2. So if they were up top, positives and negatives, and you crisscross, it would look like Mg2O2. But because just like in math, they can be divided, they can be reduced by the same number, not one, but a different number, you can reduce it to an empirical formula. So instead of having Mg2O2, because the 2's cancel out, I'm left with MgO, or magnesium oxide. Mg or magnesium 2, oxygen 2, and magnesium oxygen are not the same formulas, but they do suggest the same ratio. So it's a 1-to-1. So for every one of these, you get one of these. For every 2 of these, you get 2 of those. Same thing. They're not the same formula. We'll see that a little bit later in the next unit. But again, it's the same ratio. MgO is the empirical or the simplest ratio formula. Ionic formulas are generally reduced to the empirical formula. Okay, so exercise real quick. Using oxidation states, write the correct formulas for the following ionic compounds. You've got zinc and sulfur, sodium phosphorus, and then you're going to write the empirical formulas for C6H12, O6, C3H8. So looking at zinc and sulfur, you're going to end up being ZnS. And then sodium phosphorus. So sodium is a +1, phosphorus is -3. The 3 doesn't cancel out because you can't divide both by 3. You can only divide by 1, so you leave it as is. Whereas the zinc and the sulfur, you can cut it down. And then making the empirical formula, all you have to do is find the lowest common denominator and divide by it. So in this case, you got 6, 12, 6. You can divide each by 6. So you should get 0, 2, 0. C3H8 cannot be divided by anything but 1. So you leave it as is. That's the empirical formula. All right, so nomenclature. There are 2 types of ionic compounds. You got the binary, which we've already seen. That's one element, one element. And then you have the tertiary or ternary. They contain 2 elements, or an element and a polyatomic ion. Now, binary ionic compounds, simple. You name the metal, and then you have the base name of the nonmetal, usually ide. Like KCl is potassium chloride. Na3P is sodium phosphide. Pretty simple. Even though the sodium phosphide contains 4 ions, it's still binary. We don't have to do anything specific with that. So as you're looking at that, the really easy ones, you have the metals that form only one type of ion. That's what we've been seeing, potassium, sodium. It's either +1, +3, +2. Those only have one positive charge. So you name the metal, and then you name the nonmetal with ide at the end. Now there's the second type of metals. These are the ones, usually the transition metals, right in that middle. They have more than one. You've got like +2, +3, +2, +4. And so this is special. What you're going to end up doing is you're going to name that metal, and then in parentheses, in Roman numerals, very important, you do Roman numerals only, and you don't put a number there because that could be confused with the number of elements that are in that compound. So make sure you only use Roman numerals in the middle. Now, the best thing about this like the easiest thing, is you take the metal and the charge of the metal, that charge, the number charge, goes in that parenthesis. And then you give the base, which is the nonmetal ending with ide. So this is called the stock system. It's required when using metals with more than one oxidation state. You're going to have a combination of iron and chloride can yield more than one compound, because the iron can, this is what I was talking about, the +2 +3. So iron has a +2 charge and a +3 charge. When you add it with chlorine, which is a -1 charge, you could either get FeCl2 or FeCl3. To name this, you're going to look at those charges to figure out what is going in the parentheses. So in this case, a Roman numeral is inserted after the metal indicating the particular charge in that compound. So FeCl2 is going to be iron 2 chloride. You see how that 2 is used in there? You're going to use it after the iron to indicate the charge. And FeCl3 is iron 3 chloride. All right, so exercise real quick. Looking at this, you've got gold. There's two types. You got +1, +3. So the +1 is going to be gold 1 oxide. The +3 is going to be gold 3 oxide. And notice, again, don't put the number down. Don't put a 1, don't put a 3. Put the Roman numeral. Very, very important, because if you put a 3 in front of one of these things, it could indicate how many elements are there, and you don't want that. All right, so Roman numerals always attached to the metal. Most nonmetals have only one negative oxidation state, so we don't have to worry about that. There is one nonmetal that has more than one possible negative oxidation state, and that's nitrogen. In ionic compounds, nitrogen is going to carry that -3 though. Okay, so then we lead to the ternary compounds. So we're going to take another step. We're going to involve polyatomic ions with this. That you can find right here. It'll be table E, page 2 of your reference table. They're called tertiary ternary compounds. They involve polyatomic ions. All of these right here, all of those are polyatomic ions. And polyatomic ions, let me move myself real quick, are ions that consist of more than one atom. Within a polyatomic ion, the atoms are covalently bonded. So you're going to look inside, and these are all covalent bonds. But they form together to make an ion all on its own that attaches with the metal, making an ionic compound. So when these ions combine with a metal, the ionic bond is formed. Most are negative, and most end, you'll notice, with ite or ate instead of that traditional ide. The subscript in the polyatomic ion should not be changed when writing formula compounds. So in this case, like you've got CO3, do not mess with that 3. You got to leave it alone. It's part of that polyatomic ion. Put parentheses around it so you know that it's all combined into one thing. All right. So sodium sulfate. What this looks like is you've got sodium, Na, it's a +1 charge, and a sulfate ion. And sulfate can be found right here, SO4, 2-. So again, what you're going to do is you're going to crisscross. Now the 1 goes over here, leaving it with just the regular polyatomic ion. The -2, you're going to take the 2 and you're going to cross it down here. So it's Na2SO4. And then you got magnesium chloride. So here's another thing. Another big reason why I always put parentheses for polyatomic ions. This one doesn't have one. I'm not sure why. I don't like it. I would rather have it, but it doesn't. So in this one, you see the parentheses as I use them. Magnesium has a +2 charge, and chlorite, ITE, which is right here, has a -1 charge. You crisscross, and you're going to notice that you're going to need 2 chlorite ions, polyatomic ions, to match up to fill the 8 octet for the magnesium. Okay? Because you need 2, make sure you have that parentheses and put a 2 down there. That means you need 2 of these ions. All right. So, ooh, something's hidden back there. I don't know what it is. Give me a second. Okay, so iron 2 sulfate. See, like there's that too. Love it. So you know it's iron plus 2 sulfate, or sorry, sulfite. And I'm going to go over here. Ite is a negative 2. So plus 2, negative 2. Meaning that when you crisscross, you've got 2 and 2. They can be reduced because they can both be divided by 2. So you're left with FeSO3. Remember, you can make the empirical formula by this and makes your life easier. You don't have to have so many numbers in there. Just do it. All right. So potassium oxalate. Oh, I really hate that that's covered. All right. Potassium plus 1. Oxalate C2O4 minus 2. So again, I don't like how there's no parentheses right there. I typically do this. And so I would put parentheses there, again, indicating that this is a polyatomic ion. It also is like, gosh, it's an ion. If it's an ion, I'm not going to mess with it. I can't mess with those subscripts. I can't reduce it down. Because you'll notice that 2 comes over here, and you're like, oh, but Miss Co, there's a 2, and a 4, so I can reduce it down to KCO2. We can't do that because you can't mess with those polyatomic ions. You can't mess with the configuration. So you leave the configuration whole together, which is another reason why I'm so big on those parentheses. All right, so here's some unusual ions. We've got these two right here. And you'll notice right here, they are the exact same thing, but written in different ways. It's acetate. And it is written because of the different compounds they make. So in this case, we are using, sorry, I'm moving something out of my way. We are using the ionic compounds. We're going to want to use this first one right up here. But when we get to the organic compounds, we'll want to use the second one. So you don't have to worry about that. Organic is going to be like way towards the end of the year. So we're going to look with that first one. So stick with the first one when we're doing ionic compounds. All right, a couple ones we have. We've got cyanide, hydroxide, and peroxide. So these all end in "ide." Again, you're going to see them. I'm trying to find. There's peroxide right here. You got hydronium. That's a different one that's not on there. Also, ammonium. That's not with ides. Dimercury. I'm trying to find my ides. There's the cyanide right there. Some of them are, they've got the ides in there. Just double check to make sure what you're writing on there. So sodium hydroxide would be NaOH. Ends in "ide," not binary, because you got that polyatomic ion. Make sure you know polyatomic ions make it a tertiary or ternary compound, not a binary. There's your ammonium. It's a positive polyatomic. Its compounds often appear to be binary. By name, since it's positive, it's named first. So ammonium chloride. You've got that nonmetals ending with "ide, and it starts with ammonium. But it is tertiary because you've got more than 2 elements. Remember that. All right. Then you've got the compound ammonium chloride. May not appear to be ionic since it lacks a metal, but the ammonium structure is an ion. So it carries a charge, what causes it to be an ionic compound. Fused ions. So you've got mercury and oxygen. So dimercury is an HDHE or mercury, and it makes a +1 charge. So that one's very specific. It's up here, right there. And then you've got peroxide, which is 2 oxygens right here. It's actually -1 charge. You've got two negatives charges, which causes a -1 charge. Just go with it. All right, let's look at this exercise real quick. We got cesium thiocyanate, strontium, nickel. So this is what they're going to look like. Again, I would put parentheses around them. All right, so I'm going to stop right here, and this is going to be part 2. If you have any questions, please feel free to ask me, and I hope you guys have a great day.